SwayamPrabha. Digital India. Educated India.
Welcome to the course Introduction to Uncertainty Analysis and Experimentation. We are on module 5, which is Uncertainty in a Measurement, and in this lecture we will continue where we left off in the first lecture on basic procedures and look at the different ways in which standard uncertainty in a measurement can be established. In the previous lecture, we saw the full detailed method for calculating the standard uncertainty in a parameter or a measurement xi, which is given by the symbol uxi, and we followed this first relation. This was as per ASME PTC 19-1, and we said that we need some readings and some information, and from that combination we can estimate the uncertainty in the measurement. The alternate to this method is what is specified in the ISO standard GUM, where uncertainties are classified as type A uncertainties and type B uncertainties. So, I encourage you to get this document. It is free, available on the web, and you can search on keywords JCGM 100, guide 98-3, or you can just put ISO GUM and you can download the PDF. This is a fairly exhaustive document, as I have mentioned earlier. And now we will look at those aspects which are related to what we are learning in this course. Now, look at the vast sweep of this standard. It was prepared primarily by BIPM, International Bureau of Weights and Measures, which is the international body governing everything related to measurement and its applications. So, that document was put together by people from all these professional organizations representatives, which are listed here and taken from the standard. We will just go through this quickly to get an idea how widespread is the use of uncertainty analysis in science and engineering. So, besides BIPM, the other organized body that was with in the formulation of the standard was IEC, which is the International Electrotechnical Commission, a body that makes standards on all types of electrical, electronics and communication related standards. So, whether it is a power supply or whether it is a Wi-Fi connection or Bluetooth, all of that is governed by some standard of IEC. So, this is a very big body which encompasses a lot of technologies. Then ILAC is International Laboratory Accreditation Cooperation. So, two things are there in this one: laboratories and accreditation. So, when we are talking of measurements, I have made a couple of references to a standard measurement or a standards laboratory. So, that is where this organization comes in. What is a laboratory? What is the standards laboratory? What are the processes by which we ensure that it is a certain quality or certain level of laboratory? That is this organization. Then you have this organization which is from physics, International Union of Pure and Applied Physics. So, all physicists also were on board in this effort, all applications related to measurements in physics. Then you had IFCC, which is International Federation of Clinical Chemistry and Laboratory Medicine. In today's time, if you are looking at COVID-19 test methods, instruments, their calibration, their certification, their reliability, it would be an organization like this which would come into play. And for them also, this whole thing about uncertainty is very, very important. Then of course, we had the major international standards body, the ISO, International Standardization Organization, and this covers practically everything, which is a very large number of applications on which it makes standards. Then you have IUPAC here, International Union of Pure and Applied Chemistry. So, the whole professional body of chemists was on board in making this standard. And the last one listed here is OIML, International Organization of Legal Metrology. This makes all standards related to measurement of various things, whether it is your petrol being dispensed at a pump or even industrial sites where you say, okay, how much coal did you give me in a coal wagon? That measurement is governed, is the processes for that measurement are governed, made by OIML, and there also uncertainty comes in a very major way. Besides these, we have already seen that this standard got homogenized with ASME PTC 19.1. ASME is American Society of Mechanical Engineers, and this standard is now a mother standard for many other applications, including aeronautics and astronautics and several other things. This standard also got adopted and became an American national standard, which is given a number ANSI, American National Standards Institute, and this also is practically drawing this and ISO gum. So, for small differences, if you leave those aside, all these standards are now pretty much the same. If we learn one, we would have learned the method for all, and the importance comes out from this slide, that what we have learned is not just applicable to the work we are doing today, but maybe in the future if we are going to do some work, it will be applicable there also, and also to various fields, including here electrical engineering, electronics, communication, physics, laboratory accreditation, laboratory medicine, chemistry, legal metrology, everywhere what we are learning is uniformly applicable. So, that the document is there on the web, freely downloadable. Please go ahead and have a look at it. These are the cover pages. This is your GUM as JCGM 100, and the same thing is published here by ISO as guide 98-3. The two are exactly the same documents, both are available, you can read either of those. So, this is guide 98-3 and it is called ISO IEC guide 98-3. Now, according to this guide, sources of error are classified as type A and type B. Type A errors or causes of errors result in an uncertainty which is evaluated by statistical methods. So, type A errors are those where the numerical value of the uncertainty is evaluated by statistical methods. Further, what we mean by statistical methods is that we have observed data, observed frequency distribution, that means data that we collect, present it as the frequency distribution. From that we derive a probability density function, and from there we get the standard uncertainty. So, the standard uncertainty for type A errors is obtained from a probability density function derived from an observed frequency distribution. So, this is real data from which we made a frequency distribution and then calculated all the statistics. This we will denote as x subscript x I comma a, s x bar I comma a, and this is also what the GUM says. The data from which it is calculated could be current or past data or a combination of those. So, there will be elemental sources of error on this count. So, type A elemental errors, they could be j in number, and we could qualify this as SXI A with a subscript j. So, that is an elemental uncertainty that is coming in x bar I, which is the measurand, type of error A, j denotes how many sources of error are there, and from each one of them what is it that we are getting. So, you will get x I A 1 first source of error, x I A 2 second type A source of error, and so on. Each one of these came from a probability distribution function from measured data. That is the important part. This is real data from which we are getting these numbers. And we can combine all of this in this formula here, which tells you that the type A standard uncertainty is 1 upon square root j s x I a j square, its summation over all the elemental sources and its square root. So, that is how we can evaluate the type A standard uncertainty. Type B uncertainty is somewhat different. So, in type B, numerical value of the uncertainty is evaluated by what is written as other means. That means, other than statistical methods based on recorded data, and data we mean measurements data. So, in type A case, we actually got some data by doing an experiment and then interpreted the uncertainty value. In type B, we do not do that, and we say I will only look at data that I have or information that I have, and then I will proceed. And the way you proceed with that is that this standard uncertainty is obtained by assuming a certain probability density function based on subjective probability. So, what it means is, for example, if I have accuracy and somebody says my accuracy is plus minus 1%, then we can convert this into a standard error by assuming that the data from which this came comes from a certain distribution, could be a normal distribution or a triangular distribution or a rectangular distribution. Assuming that distribution, and we make some more assumptions and say what does this mean, and then assign a standard uncertainty to this. So, in terms of a distribution, we said that standard uncertainty is nothing but the standard error. So, although the technique could be statistics based, the data is not from a hard experiment. So, what we do is we interpret the values from a set of reliable information or a pool of reliable information, like accuracy is one, linearity is another, and there will be so many other things that come in. And assuming a certain probability distribution function, we interpret that data in that light and calculate the standard uncertainty. We will see more examples of this in the next lecture, and that will give a flavor of how an issue like this is resolved. It is another case that if in measuring this accuracy we collected data and that data is available to us, then from that data whatever error calculation we do, a standard error calculation we do, then because it was based on actual data, it will end up being a type A uncertainty and not a type B uncertainty. But that is generally not the case as in the type of work we do. The point is then that there are certain things which, depending on how one did it, could be classified as type A or as type B uncertainties, and that does not really matter, it is fine. So, type B standard uncertainty we do not get from a type B standard uncertainty in a measurement. We give the symbol B xi comma, this should be a B. This is given as uxib in gum, and I put this in red simply because this causes confusion in the symbols, and this is one of the issues with gum and why I am following PTC 19.1. U, we have already reserved this symbol for standard uncertainty in a measurement, and so for systematic errors we got the letter B. For type B uncertainty calculations we are giving the same symbol B, and we are keeping the symbol S for uncertainties that came from data that were random uncertainties or type A uncertainties. So, there is a difference here. Okay, so then this is not the case here actually. We do not get from past data, this should not have been here. BXIB is contributions from elemental type B sources of errors, and we say the number of elemental sources of type B errors is k. So, 1, 2, 3, 4 like that k, and denoted by the variable small k. And from each elemental type B error source, we can get the standard uncertainty as this for the xi parameter type B uncertainty, and k is the number of type B uncertainty sources. And using this relation here, which is the sum of the squares and the square root of that, gives us the type B uncertainty, the standard error associated with type B uncertainties in the measurement. So, we got that, and now we are ready to calculate the uncertainty in the measurement. So, this is the combined standard uncertainty or just the standard uncertainty, which is the sum of squares and the square root of these two types of uncertainties. So, this gets us to the same point that we got in the first lecture by looking at random and systematic uncertainties. So, that is the difference between the ISO approach and the PTC approach. The ISO GUM gives a comprehensive background to a lot of things and relies very heavily on statistics and symbols used in statistics, and also the standard terms used in statistics. Now, some of those things are fine up to the point, but after that when we start looking at experiments where you have multiple measurements, multiple results, multiple sources of elemental errors, then keeping track of the symbols does become an issue. And that is the reason why I have developed a consistent manner of putting symbols and their designations, and that is more consistent with PTC 19.1. Otherwise, ISO GUM is in a way the mother standard for everything. I have reproduced here from page 8 of the standard a few lines which I will read out, and it gives a perspective on what uncertainty analysis is all about. And it says, although this guide provides a framework for assessing uncertainty, it cannot substitute for critical thinking, intellectual honesty, and professional skill. In the end, the human being, the experimenter, is the key in this. It continues, the evaluation of uncertainty is neither a routine task nor a purely mathematical one. It depends on detailed knowledge of the nature of the measurand and of the measurement. The quality and utility of the uncertainty quoted for the result of a measurement, therefore, ultimately depends on the understanding, critical analysis, and integrity of those who contribute to the assignment of its value. So, after all this calculation, when we do get UXI, although it came out through a very involved mathematical exercise, as it says here, this is ultimately coming from an understanding, a critical analysis, and integrity of the people who report it. So, it is not something which is very, very rigidly fixed in some sense. This thing also requires, as I mentioned in one of the lectures, that we should be always conservative and of course honest in reporting what the uncertainty is. Conservative means we always report on the higher side. It may it may show us in a slightly bad light, but it does not matter, at least we are being honest. So, with that we summarize what is there in the ISO approach. Now, we move on to examples, and these are examples on measurement uncertainties. We have 3 examples, we will take them one by one. Here is the first one. The application is that there is an electric cable. Around that we have put an instrument which is a voltmeter or a multimeter, and we are reading the voltage based on the way it picks it up. This takes the current, and there will be another 2 links which are connected between the supply lines. This is, say, the live and the neutral or earth, and we are getting the voltage between these 2. We can do that quite routinely in any of our domestic wiring or anywhere else. You just get the right instrument, put it and take it. So, this keeps showing a digital value, and if you actually see the voltage, you will find that there is a slight variation all the time. You just do not get a rock steady constant same number. So, this is the application, and I have said that these were measured over a certain time period. This is 5 minutes, it does not matter 5 minutes or 5 seconds or 15 minutes. At some random times during that period, these readings were noted. When you say readings were noted, means you say, okay, now I will look at it, and even if the reading is fluctuating, whatever I see, I will record it. That is what we did. So, these are the numbers that we have got. They are all listed here, and the question that you have been posed is calculate the nominal value of the measurement and its random standard uncertainty. Okay. So, what we have been asked to do, nominal value of the measurement means x bar. All the while we have been using xi bar. This could be x1 bar, or since there is only one measurement we are working with, we can even call this x bar. So, that will tell us the nominal value, and the random standard uncertainty, this is the symbol as we have got is S xi bar. In this case, we can just call it S x bar. So, those are 2 things we need to calculate. So, let us see how the procedure is. Okay, so we have all those numbers and our procedure would be like this. We have the data points and we can call them, say we will call it x1. So, the data points are x11, x12 and like that up to x112. So, our sample, this is our reading sample. Sample size is the number of readings we have. We will call it m or mi. This is equal to 12. And to get the nominal value, we just need to calculate the mean x1 bar. And if you do that, just do the arithmetic mean, do the calculation and you will get the answer as 240.4. So, we do an important thing, we round off and report it to something that makes sense, and since our measurement was only up to 1 decimal place, we will say that the mean value is 240.4 volts. Whether the next digit makes sense or not, it is the standard deviation that will tell us. For doing that, we then calculate the sample standard deviation Sx1, and this is 1 upon square root n minus 1 summation xi minus x bar square x1 j. So, this is j equal to 1 to 12. And if you do this calculation, you will get 1.368 volts. We could round this off and say this is 1.4 volts. Now, before we proceed further, when we are dealing with data, we need to do one check, which is Chauvinet's criteria, or in general what this is called a outlier treatment. So, this thing can be done either by using Chauvinet's criteria or by a tau based table. I will show it with Chauvinet's criteria. So, what this criteria tells us is that if you have these readings, then if you look at the absolute value of the normalized deviation, which means the di is defined as xi, which is the reading, minus x bar over the standard deviation Sx. Then, according to this criteria, the absolute maximum value must be less than something which depends on the sample size. So, our sample size is 12, and if you look up the table on Chauvinet's criteria, 12 is not listed. It says that for 10, the maximum allowable possible deviation is 1.96, and for 15 sample size, this is 2.13. So, what we do? We calculate what is the deviation for each reading with this formula, and after doing that we see, well, what is the biggest number that we get, and if you do that, we get a biggest number which is D I max comes out to be 1.58 volts. Allowable if we take a more stringent 10 criteria, 10 sample size criteria, we are still within that 1.58, less than 1.96 and obviously less than 2.13. So, what it tells us that all our readings are statistically expected. So, nothing needs to be rejected. So, this is no rejection. So, we keep all those 12 readings and go ahead, and now our job is to calculate x1 x bar, which is the standard error or standard deviation of the mean, which is Sx1, which is the sample standard deviation divided by the sample size, which is 1.368 divided by square root of 12, and this turns out to be 0.3949 volts, which we round off to 0.4 volts. So, we got what we were looking for. We got the nominal value x1 bar as 240.4 volts, and the systematic standard uncertainty as 0.4 volts. So, this is not systematic, this is random. This is the mean, or we may call it nominal value. So, that is the answer. Now, we come to the next example. It says the systematic uncertainties in the measurement of the average temperature of a water bath are as follows. Due to calibration of digital thermometer 0.3 degrees Celsius, due to environmental influence on digital thermometer 0.005 degrees Celsius, due to heat transfer between thermometer and ambient 0.002 degrees Celsius, due to spatial non-uniformity of the water 0.05 degrees Celsius. And it says calculate the systematic standard uncertainty in the temperature of the water bath. So, what this thing tells us is we have to calculate B. There is only one measurement, we will call it x1, or let us call it in this case x2, B x2 bar, this is what we have been asked to calculate. And the systematic standard uncertainty arises, as we know, from elemental standard uncertainty, from elemental errors, elemental systematic error sources. In this case, we have 4 of them. So, what we do is we call it the first one, this one, B x 1 bar, x2 is our parameter, and this is the first systematic error source. So, B x 2 bar 1, this is 0.3 degrees Celsius, B x2 bar for the second reason is 0.005 degrees Celsius, B x2 bar 3 is equal to 0.002 degrees Celsius, and B x2 bar 4 is 0.05 degrees Celsius. We take it that the systematic uncertainty that is being given here is the systematic standard uncertainty, and that is why we wrote down these 4 values. So, now let us see what the solution will look like. The relation that we got to use is that the systematic uncertainty in a result, the systematic standard uncertainty in the result is the sum of squares of elemental systematic standard uncertainties from all the sources. In this case, we have 4 elemental sources, k is equal to 4. The values have been given, so we can open up this, and finally, this is all square root of all this. So, b x 2 is equal to square root of the square of all those terms that we had. (0.03) square plus 0.005 square plus 0.002 square plus 0.05 square and square root of all of that. And if you do this calculation, you will get 0.58557, and you can put more decimal places, which we round off and say this is 0.6 degrees Celsius. So, that is our answer, that the systematic standard uncertainty in the measurement or in the measurement of the water bath temperature this is equal to plus minus 0.6 degrees Celsius. So, that completes our solution. Now, we come to the third example. It says 7 readings were noted while weighing a fuel pellet sample on the same balance, and these were this grams. The systematic standard uncertainty in the measurement is 0.0001 grams. Calculate the standard uncertainty in the mass of the pellet and the uncertainty at 95% confidence level. So, to give a background of this measurement, what we have is we make a fuel pellet. We say, for example, you have some agricultural waste. We take that, make it into small pieces and compact it and make a pellet. So, this will be like about 10 to 15 millimeters in diameter, and length would be like 20-30 millimeters or even less. And this is then used as a fuel. So, we have to do many things with this pellet, and one of the things is we have got to measure it and measure its mass. From a practical applications, more than mass, the calorific value of this would be of real interest. We will come to that later on. So, what we have been given is some readings that the same pellet was put on the same balance and hopefully by the same person who was operating it. That's how these readings were taken. And so, we have been given these 7 readings, and this becomes that this will get readings will be x. So, let us call it parameter x 3. What we have is x 3 comma 1, x 3 comma 2, and so on until you have x 3 comma 7. Sample size m is equal to 7. So, what it tells us that we can use this data to estimate the random standard uncertainty. That we saw in the first example, we will follow a process very similar to that. What it also tells us that systematic standard uncertainty in the measurement is this much. So, systematic uncertainty means this is B in the measurement Bx3, and this has been given as 0.0001 grams. So, our procedure would be that from this first set of numbers that we have, we will calculate Sx3 bar, then we will use the formula Ux3 bar, which is the standard uncertainty in the mass of the pellet. This is square root Sx3 bar square plus Bx3 bar square root of all of that. And it says what is the uncertainty at 95% confidence level? Uncertainty is Ux3 bar. We have been asked at 95% confidence level, so it is 95. This will be KCl times Ux3 bar, which for 95% this factor is 2. So, this becomes 2 times Ux3 bar. That is the second part of the question here. So, let us solve this now. So, we have all those readings and the sample size is 7. We do exactly what we did in the first question. We calculate the sample mean, which is our mean value, average value, or the nominal value of the mass. And this we can do the averaging calculation, and when you do that, you will get 5.147 grams, which we could round off to as many decimal places as was given to us, which is 5.14. We will keep as this much. Then we calculate the sample standard deviation, which is S x3, sorry, not x3 bar, just x3, and this the same formula is applicable. We can put it in a spreadsheet or write a code, or there are automatic things in the calculator these days, we can use that, and from there we get this as 0.00111 and 2697. I am deliberately putting that many number of things, so that this is what the calculator showed, but we know we got to round it off, and this we will say is 0.00111 grams at the most, or we can even delete that and say 0011 grams. Then we do the same thing, outlier treatment. For m equal to 7, the maximum possible deviation, this is given in the charts as 1.80. So, this comes from that chart. You can look up statistics notes, books, web, anywhere else. And we do the same thing, calculate the deviation for every measurement, those 7 measurements, and pick out the maximum size out of it, and we get that in our case this is permissible. In our case, di max as measured is 1.54. We are well within this limit, so all readings are acceptable. So, we proceed further. We do not need to do any more other calculation. We calculate the standard deviation of the mean, which is our standard error or standard uncertainty, S x 3 bar, which is S x 3 by square root m, which is 4.2056 into 10 to the power minus 4 grams. We could round that off and say this is 0.00042 grams. So, then we come to the expanded uncertainty. Now that we got this, u x 3 bar is 2 times, sorry, now we got this, we have already got b x 3 bar which has been given to us. So, we can calculate u x 3 bar, which is square root s x 3 bar plus b x 3 bar square. This is square root of this number square, 4.2056 into 10 to the power minus 4 square, plus b x 3 bar is given to us as 10 to the power minus 4 this square, and when you do this calculation we get the answer 4.3228 into 10 to the power minus 4 grams. And then in the next step we have to calculate u x 3 bar at 95% confidence level. This is 2 u x 3 bar, which is 2 times that number we got, 4.3228 into 10 to the power minus 4, which is 8.6456 into 10 to the power minus 4 grams, which we round off to 0.00086 or 87 we can say, or even 0.0009 grams. Either of those would be okay. So, that completes our solution and we got the answer that we were looking for. So, with that we conclude our discussion on measurement uncertainty, where we have seen two methods. First, the PTC 19.1 approach, which we shall follow, and now we have just learned about the ISO approach, which gives us type A and type B uncertainties. And I also presented a few examples to illustrate what we have learned so far. What the discussion of ISO GUM has thrown up is about type B uncertainties or the systematic uncertainties. Mostly these would be systematic uncertainties. In fact, ISO GUM says that the word systematic uncertainties could be misrepresented or misinterpreted, so they do not recommend it, but simply it is easy to use, so I have kept it, and this is as per PTC 19.1. So, what we just came across when we looked at the ISO definition of type B uncertainties is that we have information, we assume a certain distribution, and from there we estimate a standard uncertainty. So, this information, as I mentioned, there was accuracy, there is linearity, there is resolution, all these things are coming in. The question is, how do we convert that data into a standard uncertainty? So, this would end up being some sort of a Bxi bar, comma k, the elemental systematic standard uncertainty. This is what we will pick up in the next lecture, where we look at special cases of systematic uncertainties. On that note, we conclude this lecture, which was on the procedure for calculating measurement uncertainties. Thank you.